sharing again.
Yeah. Sorry, I should be back up and running. Yeah, thanks, Meaty. Okay, let me see how it's going. Just launching a, well, actually, I'll wait a minute to launch the poll because I see everyone's busy building things. So I think I know the answer to the question. So even if you are building, by the way, it's really helpful if you have your camera on, just so I can actually quickly see who's doing what. I mean, unless you finished building and went and got coffee or something, but.
Is it worth trying like a 1 mega ohm, or am I just gonna get all noise if I do that?
Oh, I see. Maybe you need to do.
Yeah, you can try for sure. Yeah, and just whatever you've got. I don't know if you have any 1 mega ohm resistors. You probably have some 100K. I just wanted to get you a sense of how you know, how the resistance impacts the signal.
Is the signal supposed to like change so much with how close the object that's how close the object is to the sensor?
Yeah, I'm not sure what you've set up. So I was just saying, just set up the photo transistor and not the reflectance sensor. But if you've done that, that's fine too. Yeah, but I was just imagining you sort of see your room lighting. You know, so when you cover up the phototransistor, the voltage would in this case it's the other way around, right? In the dark, let's see, no current. Yeah, in the dark, if you've set it up the way I have, in the dark, the voltage should be low, and as it gets brighter, the voltage goes up. So by covering it with your hand, the voltage should drop.
Gotcha. Yeah, I just have the the one that basically looks like a black LED.
Yeah, that's it.
Is that?
Yeah.
That's the photo. Okay, perfect.
So when
yeah,
you,
so I noticed when I like whatever I'm holding next to it, the closer it is to the sensor, it seems to make a difference to the signal. I'm just wondering if that's like an inherent part of it, or
yeah, it should just be that you're blocking light from your room lights or sunlight, whatever's in your room.
okay, I see. And is the exposure, or sort of, I don't know if this is the correct word, but like sort of the intake, the sensory intake, is that like omnidirectional or in all directions, or is it like straight up?
Well, that's actually in the spec sheet. I think I'll show you for a previous device. I have it in my slides for the OP805, which is what we used to use. But the one you've got is probably pretty similar, and it is directional.
Okay.
Yeah, it has an acceptance angle. Yeah.
Thank you.
Yeah, I'm just going to run this poll and see how many of you are done.
Andre,
Yeah.
I have a different sort of electronics kit. I didn't buy the one from the lab, or sorry, the one on the shopping list.
Yeah.
But one of the things that was included in this kit I got is a photoresistor.
Yes.
That's totally different from what this is, right? But
Yeah.
it seems like it has similar functions. So I'm wondering why a transition instead of a resistor.
That's a good question. Whoops, sorry, I'll mute you because I'm getting some echo. But I think a phototransistor is potentially more sensitive. A photoresistor, and I know I've got one as well from that kit. It looks like a little, it's a little photocell. It's got a little, we can put it under the camera or something. Let's see if I can find one so I can show everyone. Because yeah, anyone that's bought the kit from AliExpress ought to have one of these.
It's got like that squiggly line.
Exactly, yeah. And what these are, yeah, this is a light, a resistor that varies its resistance based on light. So, yeah, it looks like that. That's maybe not super obvious. Okay. Anyways, yeah, with a phototransistor, I think you can generate a bigger signal. Does that make sense, right? Because I mean, depending on what load resistor you put on, you can adjust the signal up and down. So, I mean, I guess you could do that to some extent with a photoresistor. But yeah, I have a feeling that the phototransistor is more sensitive. That's my guess, though I'd have to check.
All right, cool.
Yeah, but these little photosensitive resistors, I think, are what's used, for example, in street lights to know when they should turn on, right? Or if you have some of these outdoor motion sensing lights that check for ambient light before they activate. So I've got some, for example, that they're only on at night, and they check by having these little devices. I think these are quite a bit cheaper too. But they just check for overall ambient light. They're also, I should also say, I think the infrared phototransistors are sensitive in the infrared, and I think these little guys are sensitive to visible light. So you can still use these potentially as a navigation system for your robot, but I think they would home into like a light bulb, not an infrared beacon.
For the light source, do we connect these light bulbs, not the regular green ones, right? infrared?
Yeah, I think that's an infrared LED. Yeah. Yeah.
Would it not work if we used regular light bulbs, like the green?
Like an LED.
Yeah.
No, it won't, because the LED's wavelength is going to be very different from what the phototransistor expects. So let me jump to this for a second. This is a spec sheet from a different phototransistor, to be fair, but will have similar properties to the one that you've got. And first of all, you can see there's a collector current under a certain amount of light based on the angular displacement to the source of light. So they are definitely directional. They take in light between plus or minus 15 degrees, I think, at least for the OP805. You should look up what the spec sheet is and the specs for the QSD. What is it? QSD 124 or whatever model of phototransistor you have. But somewhere in the spec sheet, it will also tell you over what wavelength it'll accept light, how it will respond to wavelength. That's not on this slide, but it should be in the spec sheet. But Olivia, I'm pretty sure it won't overlap whatever the green wavelength is from an LED. Yeah, it'd be pretty different. This one's saying wavelength is 890 nanometers is how they tested it. So definitely into the infrared. Green is, I don't know off the top of my head, but green must be, what, around 300 nanometers, 400 nanometers? I think red is around 600. Yeah. Okay, well, look, folks, I think I'll move on. It looks like well over half the class has got this finished. There's a few people still working on it, and I have a feeling there's a few people that went and got coffee because they got done a long time ago. So I think we can move on. Of course, if you didn't quite get done with that, again, this is roughly what you're doing on Thursday, so don't worry about it. We'll just keep going on Thursday. You can play with it afterwards. And as always, I'll post these notes in the calendar after this lecture, so you can go back and have a look. Okay. Did anyone have a chance to try different resistors and see how that worked out? Yeah, Tristan, how'd that go?
Yeah, the 100K was right about right. There was lots of movement. You actually saw a good change.
Yeah.
1K, there was barely any, and Mega, you were like just
massive.
locked at 5. Yeah. There was hardly any change down from 5.
Yeah. Okay, good. So, and that was just, again, there, you're just detecting whatever infrared is bouncing around in your room, right? Assuming, unless you set up a beacon. Yeah, no, that's good. Okay, so let's talk about something a little different. Well, no, I mean it's continuing from this, right? So we're starting with this circuit. Okay, so let's say we're going to use 3.3 volts. We've got a load resistor. We'll call that 100K or whatever you want. And now we can connect this straight to the blue pill, right? Or not? So there's an issue if we just do this. Can anyone guess what issues there might be in the context of trying to detect a relatively faint beacon at a distance?
Lots of noise.
There will be noise. Yeah.
Give me the tracking low, and we need to boost the signal.
Sorry, I missed a bit of that. Please repeat.
We need to boost the signal.
Yes. Yeah. You could do that with a bigger resistor, as Tristan was just saying, right? We could put a larger resistor. But what happens if you use that as a means of boosting your signal? If you just set a large resistor in place?
The noise gets larger as well.
Yes. Sorry, there's two of you talking, but I think you're both saying the same thing, right? So, you know, in a sense, whatever background light there might be in your room will also give you larger voltage. So yeah, changing this resistor, yeah, amplifies both the background and your signal, but in the end, it may not even be enough to give you the signal that you want. All right. So okay, so that's fine. So maybe what we need to do is actually actively amplify that, right? So we can do this. Now have a look at this diagram, and you know, now, okay, so first of all, I've switched over to having 5 volts. We're going to go through an amplifier system anyways. We're not going to be operating at 3.3 volts. So I'm now protecting the blue pill with a 3.3 volt Zener diode. And I have an op amp in place with you know, significant amounts of gain. I'm not sure I've made things any better. So now I can put in lots of gain, way more than I could just by putting a bigger resistor in place. What are the problems with this circuit?
Everything's getting amplified again, noise included.
Yeah, thank you. So the original problem of amplifying the room background, infrared, whatever, that hasn't gone away. There's more gain, right? So maybe now we can at least detect a beacon that's farther away. But now I've actually added a problem. Does anyone spot it?
What happens if the Zener diode starts when you not?
Sorry, I think that was an interesting comment, but I didn't catch the whole thing.
I was just speculating that the Zener diode is connected to the positive input.
So the Zener diode, no, it's connected to ground on one side and to the output of the op amp on the other. There's a problem with this as well. It's not a huge problem, but it is not commonly done. Does anyone spot that issue?
Does it have anything to do with the voltage being inverted?
Which voltage?
Because of so there would be a current running through, or maybe I'm seeing this wrong. But would the voltage on the blue pill be negative?
No. If it tried to go negative, the Zener diode would short it to ground. And if it tried to go above 3.3 volts, the Zener diode would short that to ground. So no, the blue pill is well protected here. There's no question. How's the op amp going to feel about it?
Doesn't the op amp try and push your full current out of the output?
Yeah.
To match, or make the negative and positive inputs match? So if you're shorting that to ground?
Yeah, so look, if you're providing enough gain and the op amp is trying to put out 5 volts or even more, right? So first of all, the op amps we've provided you don't work well at 3.3 volts. You're going to have to power them off a larger voltage, at least 5, maybe 9 or 12. And if the op amp is trying to put out, say, 5 volts, and the Zener is shorting its output down to 3.3 volts to stop it, not all op amps are very happy in that mode, right? Their output is effectively being shorted to ground by the Zener diode. So some op amps can tolerate that and some can't. In any case, it's not a very nice thing to do to the op amp's output. So one of the things that's commonly done is actually a little 10 ohm resistor placed here. So when the Zener diode pulls the output here down to 3.3 volts, it's at least not totally shorting the op amp. It's just setting the load down to something like 10 ohms. Okay. in any case, that's actually not the problem I was worried about in this. You know, I drew the schematic explicitly to create an additional problem. I don't know if anyone else can see it. So let's say we've carefully selected this load resistor to be, say, 100 kiloohms. What's the load resistance on the phototransistor in this circuit?
Is it that the 10 ohms is also going, sorry, the 10, not sure what that resistor is, but that's also going to ground, so it's going to be a parallel resistance.
Yeah, Andrew, very good. Yeah. Oh, and by the way, if there's no, usually you should say 10R or something. You'll just a quick dive into nomenclature for electronics. If there's nothing after it, usually it's the base value, so it'd be 10 ohms. More commonly, you're right, be written as 10R. The ohm symbol is not often used, or at least in old electronics, electrical engineering conventions, it's not used because it wasn't a common symbol in a keyboard, right? So R is used instead of ohms, and K is used instead of kiloohms. And in fact, to avoid using decimal places as well, you'll get conventions like this, where 3V3 means 3.3 volts. If you had, say, 4K7 means 4.7 kiloohms. Right? Anyways, just a little aside. But Andrew, you're exactly right. This 10 ohm resistor is now effectively in parallel with this load resistor, because the negative input of this op amp is a virtual ground. So this circuit does not at all work the way you would have thought it would work, where you take this, whatever voltage is across this load resistor and amplify it. That's not what's going to happen, right? In fact, all the current is going to flow through the 10 ohm resistor, and the voltage that will result from that is much, much smaller than you might have guessed. All right. So it's a problem with the inverting op amp configuration, and I know you've studied op amps already, so this should be common, it should be well known to you. But once you set an op amp into negative feedback, right, by putting a resistor between its output and the negative input terminal, if the other input terminal is a ground, right, then the negative terminal is also a ground. In any case, they'll be at the same voltage because the op amp configuration forces them into the same voltage. So there's this virtual ground analysis of an op amp, which is how you derive the gain function of an op amp, also known as its transfer function. But when you start looking at things like, the input impedance of the circuit, right? The input impedance of this circuit is 10 ohms if I've set it up like this. And that loads down this circuit, all right? Basically, this amplifier is interfering with the functioning of this circuit. So that's not how you'd want to set it up. All right, so as Andrew correctly pointed out, the load resistance is now effectively 10 ohms. Okay, so this is one of a number of issues that we need to deal with op amps, because I'm pretty sure you dealt with op amps as ideal op amps. And I'd like to spend the next 10 minutes talking about all the non-ideal aspects of an op amp, ranging from gain bandwidth limitations to bias currents and so forth. Okay, and input impedance limitations are some of them. All right, so but it's 3:39, so before we jump into this, which is going to be a little theoretical for the next 10 minutes, let's just take a 5-minute break. Is that okay? So we'll be back. Let's be back at 3:45. Okay. And when we come back, please remind me to start recording again. I'll just put it on pause. Okay. Maybe I'll just give people a couple more seconds to make their way back. Okay, so yeah, like I said, I think you've all been used to ideal op amps and looking, treating them these little magical devices that amplify the input signal. And I think it's time to consider all the things that make them non-ideal, and then actually you have to think about if you're really going to design with op amps, because otherwise they'll come back and bite you. Okay. So input impedance is one of these things. Right? Obviously, in a virtual ground configuration, in the inverting configuration of an op amp, the input impedance is limited by the resistor that you place on the input. And if that's a small resistor, you end up with very small input impedance. So it's quite common to have to use the non-inverting configuration. In this case, for example, the input impedance is extremely high. Now, this is not an amplifier. This is a buffer, right? So in other words, the V-in and V-out are the same. But this is also a construct that's very useful. Does anyone know why you would use this? Right? Because this is an amplifier. This is a unity amplifier, right? It is a negative feedback, so the negative terminal and the positive terminal have to be at the same voltage, and therefore V-out is equal to V-in. Xander, thank you. Infinite impedance or semi-infinite impedance, right? What's the impedance on the output? Right, because the op amp can source power. It can source current. Does anyone know what the output impedance is? I mean, I don't know what it is in ohms either, but is the output impedance high or low? So we've established the input impedance is very high. Maybe a tricky question for you. If the op amp can source current at relatively low voltage, right? So let's say it can put out, 5 volts at 100 milliamps. Is that, yeah. Sorry, Dominic put the right answer in here. Yeah, the output impedance is low. It's a source of current. It's a power source. It's going to have low output impedance. I don't know what it is. It might be tens of ohms. It's not like really low like a power circuit. But yeah, this is basically a circuit that allows you to provide a voltage at low impedance while measuring it at high impedance. So in other words, you can measure a voltage and reproduce it in a way that you don't disturb the circuit in front of it. Okay, so you can draw current from the output of this op amp without disturbing whatever circuit it's measuring the voltage of, right? So it's like replicating the voltage from one side of the circuit to the other in a way that isolates the previous circuit so it doesn't get messed with, okay? And that input impedance, and you can look on the spec sheet, it's like 10 to the 12 ohms, right? These are field effect op amps. In other words, the first transistor that input voltage sees is a field effect transistor, right? It's one of these that has insulated gates, and that allows it to have an incredibly high input impedance. So that's a good thing to know about these op amps, okay? So if you use them in the non-inverting configuration, you can be guaranteed quite high input impedance. So that gets you away from what was happening before in the previous circuit I showed, where we were messing with the load resistance of the phototransistor by coupling it to the low input impedance of our amplifier circuit. Another limitations of op-amps that you need to know is the gain bandwidth product. So you can't just get infinite amplification from an op-amp, right? It will have some limit, and in fact, that's another problem with this circuit, right? Because what's the gain of this op-amp circuit? This you got to do in your head.
Maybe 10.
Yeah, okay. That helps.
Yeah, 100. Yeah. So, but you have the right idea. It's 1,000 divided by 10, right? So it's a gain of 100. Can you amplify 100-fold with that one op amp? Maybe, maybe not, right? So there's a limitation to op amps that's called the gain bandwidth limit, and it's a fixed number that's a spec for the op amp. And to figure out if you're within that range, right, that it can work within, you take the amount of gain you're asking the op amp to provide and the maximum frequency that you're asking the op amp to amplify. So if you're looking at a 10 kilohertz signal and you want to amplify it 100-fold, as we had in that circuit, what is that? 10 kilohertz times 100 is 1 megahertz, right? So then you have to look at that and see if it's within the gain bandwidth limit, and it actually is. Okay, it's 3 megahertz. So at a gain of 100, you can amplify signals up to 30 kilohertz. Does that make sense? So if you know the frequency you need to amplify, you divide the gain bandwidth product by that frequency, and that gives you the maximum gain to use in your circuit. But so in other words, this op amp will only amplify signals up to 3 megahertz, but at 3 megahertz you can't amplify. You can only pass it through at a gain of 1. Whereas a 1 hertz signal can be amplified 3 million-fold. Okay, but that product is a fixed spec of the op amp, and it's stated as gain bandwidth limit or the unity gain bandwidth. Right, so the maximum, at unit of gain gain of 1, what's the maximum frequency that you can put through? So that is something that you also should consider with op-amp circuits. Okay, make sure you're not exceeding that gain bandwidth limit, asking op-amps to amplify 1,000-fold for say 100 kilohertz signal or something that might go outside of its gain bandwidth limit. The other reality of op-amps is that they leak current. Very small amounts of current, they're called bias currents. But depending on your choice of resistors in an amplifying configuration of an op-amp, those bias currents can be a problem. Okay, they're not large, right? In fact, in the TL82, this is a spec sheet from the TL82, which I think is what we've given you as an op-amp. The bias currents range, right? The spec sheet is always, it's hedging its bets a little bit, right? It's saying here's what's typical, and the typical bias current at room temperature is around 30 picoamps. But in the full temperature range, in the worst case possible scenario, it can be as high as 20 nanoamps, right? Which means that basically you can have up to 20 nanoamps leaking out of these terminals and then making its way to ground one way or another, right? So for the negative terminal here, that bias current would flow through this resistor or impedance Z1. It would flow through this impedance or resistor Z2. From the positive terminal, just go straight to ground, right? But that will create voltages in your circuit you don't expect. And I've seen this happen in some of the amplifying circuits for robots in this course, where they were trying to detect a beacon at a distance, right? And use some big resistors in their circuits and managed to amplify the bias currents to produce these offset voltages that were just there all the time. It made their circuit kind of hard to get functioning right. And that's one of the reasons you tend to stay away from very large resistors in circuits like this, right? Because a 20 nanoamp bias current times a 10 megohm resistor, say you use that, a Z1, that's a 200 millivolt offset, right? And that'll basically, it'll make your circuit look like there's always 200 millivolts being detected at the phototransistor, where that's really just a construct of the amplifier and its leakage current. Sorry, yeah, I was about to answer Gus's question in the chat. Thanks, Meaty. If you exceed the gain bandwidth limit, just the gain at that frequency will be less than you think. So it'll just filter. Basically, yeah, Meaty's right. It basically filters it out. Okay. There's a trick, and if you ever see this in a properly designed circuit, and you wonder, okay, here's the inverting op-amp configuration, and why the heck did someone put a resistor between the positive terminal and ground when you don't expect current to flow there? So if you see this in a schematic, it's to try to limit the effective bias currents. Because the fact is both terminals are leaking current, and they leak relatively similar amounts of current. And you can actually balance the two voltage offsets by putting a resistor to ground on the positive side, so that that resistance is the same as Z1 and Z2 in parallel, so the voltage offset from those currents leaking to ground end up being similar, right? And now all that really matters is what's called the offset current, right? So if you look back to the spec sheet, there's something called input offset current, and that's the difference between the two bias currents, right? And that's something like a factor of 2 smaller. So by using this construct of having a resistor to generate that offset on the positive terminal to try to mimic what's happening on the negative terminal, that limits the voltage offsets created by bias currents. All right. Voltage limits. This one is actually going to be critical for you, particularly this year, because we're trying to operate at lower voltages. Last year, we were building these amplifier circuits with 2 9-volt batteries, so you had plus minus 9 volts. If you're trying to power your circuits this year from a 5-volt source, you're going to run into these, right? Which is that, the 2 wires that are not usually shown in a schematic are, plus VCC and minus VCC, right? It's basically whatever you are powering your op-amp with. And the reality with the op-amps we've given you, which are relatively cheap op-amps, is that the input voltages, right, that you're going to flow to the input terminals to get amplified, you're not allowed to have them come close to the rails, right? So whatever voltages you power your op-amp with need to be bigger in magnitude than the voltages that your op-amp actually services, right? The voltages that you're actually going to amplify. Now, again, for your op-amps, if they're powered to plus or minus 15 volts, which yours won't be, they can work with signals ranging from minus 12 to 15 volts, right? Typically. They guarantee from minus 11 to 11 volts. That's really the worst case scenario. But bottom line is that, you can't quite provide input voltages that work all the way to the rails. There is a device called a rail-to-rail op-amp that does that. Here's a spec sheet for one. And if you're going to operate with a 3.3 volt power supply, honestly, you'd want to get something like this, right? I mean, they're just a little more expensive. So you can see that here, they're called rail-to-rail op-amps because the inputs can actually exceed the voltage rails by 0.3 volts and the op-amp will still work. And that's not true of a regular op-amp. Okay, so with ours, you probably don't want to power them to like ground and 3.3 volts, because if your signal can't come to within a couple of volts of ground, basically you have no room to operate. There's nothing left, okay, in terms of headroom in the op-amp. So keep that in mind. Of course, the other thing to remember is these op-amps cannot source a lot of current. We were talking about their output impedance is low, but it's not that low, right? Again, there's such a thing as a high power op amp that can source, several amps to drive, a speaker, a motor, something like that. This is the kind of thing that would be used in a relatively cheap stereo, right? To drive a speaker. But that's not the op amps we've given you. Okay, so just keep in mind, if you're powering the op amp again to 15 volts, which is what the spec sheet is all based around, right? The output of the op amp, will be limited to like 10 volts if the load resistance is just below 1 kilo ohms or something like that, right? So keep that in mind, and don't be surprised if the output voltage of an op amp is low, if you're asking it to drive an LED, a small resistor, a motor, or something like that, and honestly, a motor would be way beyond what one of these op amps could power. It would look like a short circuit. So I know that was a quick run through some of the op amp limitations, but that's what that's really what electrical engineers do, right? I mean, a good electrical engineer will design a circuit keeping in mind all those limitations, so the circuit is reliable. You can make 100 copies of the circuit that all work exactly the same way. You're not going to end up being dependent on the batch of op amps that they happen to ship you that week, right, to build your circuits. That's a difference between kind of a hobbyist electronics, where you sort of build stuff that kind of works and that's good enough, right? You're going to use it to turn lights on and off in your room or run a little robot or something, versus making an electronics product where, these specs, like the minimum allowable spec, right? What the manufacturer of the op amp is guaranteeing you the op amp can do becomes the important spec, right? So that you don't end up with a batch that's a little bit different from the previous batch and suddenly your circuit doesn't work. Now, for you that are making prototype circuits, just keep a few things in mind. Obviously, working with really tiny or really large resistors can get you into a bit of trouble, either with low input impedances or big voltage offsets from bias currents. Try to avoid having the amplifier, create massive gains that they might not be able to tolerate, and don't drive heavy loads from them. And most importantly, keep the input voltages away from the op amp voltage rails. Okay, so that's just a few pointers for designing with op amps, keeping in mind all their limitations. Right, so this ought to be a better circuit now, right? So if we're going back to wanting to detect signal falling into the phototransistor, again, from a relatively distant beacon. Now we can put a big load resistor back in, let's call it 100K. And now we're measuring the voltage at the phototransistor without messing with it, right? Because now we're using the non-inverting op-amp configuration. So the input impedance is high enough at this terminal that it doesn't mess with the voltage at this point. So it basically monitors this voltage. It amplifies it 10-fold, no, 100-fold. 100K divided by 1K. And then clamps it with a 3.3 volt Zener. But this still doesn't solve all the problems, and I'd ask you again, except you already gave me that answer, right? Because this is also going to amplify the room noise and the room background, right? So in fact, I don't know if, in that configuration, in the inverting configuration, if you had a waveform going into the op amp that looked like this, okay? So this horizontal line everywhere is 0 volts, right? So I haven't put labels on these axes except on the first one here, right? So that's 0 volts. It's voltage versus time. And the ratio of R2 to R1 is 3. What does the output look like? And I'm not going to run a poll, but if anyone can figure it out, tell me. Oh yeah, use your fingers. Good idea, Tristan. The visual poll, for those of you that have your cameras on. I'll scroll around and see if anyone else has thoughts. We've got a 3, we've got a 2, and no one else has opinions.
My initial thought was 3 because it's going into the inverting side of the op amp. So it's going to get flipped over the x-axis and then amplified, which is what 3 looks like.
Yeah. Yeah, no, that's correct, right? So, I mean, it is being inverted, right? This is the inverting configuration. And you have to think about, yeah, the signal's being inverted. So what's high first and then low after is going to be low first and high after, which is true in 2 and 3. But there's a DC level, right? The whole signal is shifted above ground, and that DC level also gets inverted and amplified, right? So 3 is correct. And that's fundamentally the problem, right? With this circuit, even though this one doesn't invert, but it has the same issue. It's going to amplify whatever DC component just happens to be generated by background infrared light in the room. So that's not going to really help you home in on this squiggle, if that's what you're looking for, over the big DC background. Okay, so that's the problem with that circuit. So how do we get away from it, right? Well, we have to do some filtering. And, you know, I'm not going to spend that much time on this year, but I will say start now to think about frequency space versus time, right? And I don't remember if I've alluded to this with your cohort at all. But in my view, you know, one of the big intuition benefits from studying ENPH that I walked away with was being able to think in the frequency domain. So almost everything we do happens in the time domain or spatial domain, right, where you're measuring distances or you're measuring time between things. But you can also, anything that happens in time can also be thought of as happening in frequency. And even spatially, you can convert things to frequency, right? And the only thing that we are naturally used to thinking about in the frequency domain is music and sound. Because pitch is frequency domain, right? So when you're looking at a signal like this, that's a squiggle above ground. I mean, you can think of it as a squiggle in time above ground, and what you want to do is you make it a squiggle in time, you know, centered on ground. Or you can think of it in the frequency domain where there's a sine wave at some frequency and then there's a DC component of frequency 0, right? And when you start to think of it that way, then it's very simple to say, okay, well, what we need to do is actually just make a circuit that just cuts it here and cuts out anything below one frequency and allows things through above another frequency. And that will move my signal to being this, getting rid of the component of a DC, which then will center the signal around ground. So filtering is all around selection of frequencies in the frequency domain, which is one of the reasons you know, in electronics, you get very used to thinking in the frequency domain. And that's what this is, okay? So an RC filter will do exactly what we want. Because a capacitor, very much as the diagram implies, has no direct electrical connection through it. So the DC impedance of a capacitor is infinite, or semi-infinite, right? So current will not flow through a capacitor in DC. Oscillations will, right? Because as you increase the voltage on one side of the capacitor, the electric fields cause current to flow on the other side. But you can't flow electrons through it, right? Like you can cause electrons on one plate of the capacitor to go in and out of the plate depending what's happening on the other plate, but the DC impedance of a capacitor is infinite. So this effectively is an RC filter that allows frequencies to go from V in to V out, anything that's not DC, but completely blocks DC. Does that make sense? So what you really want to do with this circuit, right, is you have the phototransistor. It's going to generate a voltage that's a mix of a 1 kilohertz signal or a 10 kilohertz signal from your beacon. It's on top of a big DC signal from room light and sunlight, whatever else happens to be, you know, happening in your kitchen, right? you want to get rid of the DC component of that. So you make it just a squiggly signal and then amplify it. All right, let me actually see if I can sketch that process if this all works still. So you kind of want to go through 3 steps. Right, and again, I'm going to draw this with little graphs. So this is 0 volts. This is voltage versus time. All right. This is 0. And okay. So this is where you're probably starting with at the phototransistor. Okay, you've got a little squiggle. That's your 1 kilohertz signal. So this is all just like sunlight, and the little squiggle is the beacon. Right? What you want to do is put that through some kind of RC filter so it becomes this. Right? I drew that poorly, but that squiggle is now centered on ground. Right? And then if you amplify that, whoops, not a diode, but an amplifier. Right? And I'm going to run out of board. Now you can make it look like this. Okay? So you've effectively taken that signal, and now if you amplify it, you can make it large without amplifying all of that. All right?
I had a question.
Yeah.
So if what we're doing there is shifting the axis so that it's aligned with the x-axis,
Yeah.
how is that the same as just cutting off one part of that graph? Isn't that just cutting off the beginning part instead of shifting the whole graph?
We're cutting off this, right? So that shift, the DC level shift in voltage, is a 0 frequency component of that signal. And Olivia, thanks for asking that, because that's exactly what I mean about thinking in the frequency domain. So, right, the signal is shifted above ground. That's not something that's happening in time. It's a permanent shift above ground, right? But that shift, because it doesn't change, it's a 0 frequency component. And then the squiggle has some frequency to it. So if you plot it as a function of frequency, right, the shift of the signal above ground is this component at 0 frequency, and your signal is this component at high frequency. And by building a circuit that only passes high frequency through it, you can get rid of the DC component.
I see. So in the other diagram that you drew on the whiteboard,
yeah,
was that time domain or that was in the time domain? Okay.
Yeah, this is all in the time domain. Yeah. 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 Excellent. So what I would like you to do now is, and I'll create your, I'll create 16 breakout rooms. And I'm asking you to do something quite challenging here, okay? Which is to, on paper, do not build this. This is the Thursday lab. It will take you way more than the next 20 minutes to build this. But I'd like you to brainstorm on how to design a circuit that amplifies that phototransistor signal, the oscillating signal, without amplifying the DC background. And I will say, start by designing it using 2 9-volt batteries. So you have 0 volts, plus 9 volts, and minus 9 volts. And then if you get ambitious, try to figure out how to do that with a single 9-volt battery. And do all of that in the way that also you protect the blue pill from the 9 volts. All right, so let me get to breakout rooms.
Would you be able to make these slides available by any chance?
I will certainly after the lecture. You need them now?
I just take notes on iPads, so sometimes it's easier to just take notes on the lecture slides. But also, it has this. I can just screenshot it too.
Yeah, so it would take me a minute to upload them and stuff, so I'll do that after. But if you, I'll leave the slides up in the main room. If you need anything, just jump back into the main room and ask, and I'll pop over to whatever slide you need. Okay, and I'll pull you out of the rooms occasionally to just check and see how things are going. But you can work in your own teams. You can join other people's rooms. This is not a competitive thing. So I've just made the rooms the way you're used to having them, so you can work with your teammates if you want. But you can also join other people. So good luck.
Andrew?
Yeah.
Yes, would you mind enabling the screen sharing, please?
Oh, yep. Okay, I think that should do it.
Yeah, thanks, perfect.
Okay, perfect.
Chloe, were you just asking about the whiteboard?
Screen sharing.
Screen sharing, right. Okay, I was going to say that too. Sweet.
Okay.
Welcome to Rogers. You have one new wireless voice message. First new message. Message erased.
Okay, welcome back, everyone. I just pulled you all out of the breakout rooms. If you suddenly got yanked out of your discussions, apologize. And what happened to me? Wait a second. I have to go back. Pin second screen. There we go. Okay. Yeah, does anyone want to share with a whiteboard or something similar what they have come up with and talk us through why and how it works? It doesn't have to be right.
I can share screen.
Yeah, please.
All right, just give me a second to set it up here.
Yeah.
All right. 2 seconds. Just grab this. Right. Perfect. Okay. And sharing screen 2. Okay, perfect. let me know if y'all can see that. Oh, can I zoom in?
Yeah. Yeah, I can see it.
It's not so big. That's right. So we started out, so we've got like our 5-volt supply here. Well, it's not drawing, is it? Our 5-volt supply here coming in through the phototransistor. We've got light coming in here. I'll try my best to draw with the mouse.
Yeah.
We've got our capacitor here with the load resistor, followed by the buffer, just for isolation, because there's infinite resistance here. And then followed by the amplification. So this part in here cuts off that DC supply. And then this follower is for isolation. And then this amplifies. Without inverting, we've got it going into the positive supply here.
Yeah.
Perfect. Yeah. That's what we've got. And then as for powering, this is with the 2 9-volt batteries. Our group went with, for the positive VCCs of each op amp, we've got just a 9-volt battery going to ground. And then on the other side is just a flip. It's kind of flipped.
Yeah.
So the plus 9 volts goes into ground, and the minus side of the battery goes into the minus supplies of the op amps.
Yeah, that's perfect. Yeah.
And then this diode here is just for
protection.
Yeah.
Yeah.
So yeah, and this is our out to our supposedly Bluetooth.
Yeah. Yeah. So first of all, yeah, the battery power, that's exactly right. Powering it off a single 9-volt is much more complicated, and the reason for that is, look, once you get rid of the DC component, you have a signal that oscillates above and below ground. And you're not going to make an op amp work below ground unless you give it a significant negative voltage, right? Otherwise, you run into the input voltage limitations of the op amp, and you end up operating below its power rail, which you cannot do. So that's exactly right, the way you've set up your 9-volt batteries and the power to the op amps. I know you asked me this a minute ago in your breakout room, but in fact, do you need the buffer? Do you need the voltage follower?
Yeah, that was my question. I wasn't exactly sure, nor was our group, so we just threw it in.
Yeah, because
not entirely sure on that one.
The way you've set up your amplifying stage is also high input impedance.
Right.
So
right.
I suspect you don't need the buffer. You can just get rid of that op amp and just use the amplifier directly, because you're using the non-inverting configuration, which is high impedance. So I think this works. The reason I am hesitating is you now have effectively a load resistor on the phototransistor that varies with frequency.
Yeah.
Now, if I think through it on a DC signal, right? So when the phototransistor is conducting in DC, the top of the capacitor will go straight to 5 volts. And the bottom will be a ground. So the capacitor will have 5 volts across it. What I can't figure out is, does that clip half the signal away? And I don't know that I can figure that out off the top of my head, because when the current decreases, right, of course the voltage in the capacitor will try to drop, and that will conduct current across the capacitor, so you have that. It's just that I'm worried that this has the effect of saturating your signal at 5 volts, so that you lose a bit of the oscillating part of the signal. But I'm not sure. I could actually be wrong on that one.
Is there a more simple way about going about it?
There's another way. I'm not sure that it's simpler for me to understand. I don't know that it's simpler in terms of components. But thank you. I think this is, if it's not right, it's 90% right.
Sure thing.
Yeah. Does anyone else want to give it a crack?
Professor, can I ask you a quick question?
Yeah.
So one sort of thing that my team was we were thinking about here was that we used the initial high pass filter to get rid of sort of any systematic DC offset from the sensor, which means that we have our oscillations about the 0 volt point, and then we use the amplifier to amplify them.
Yeah.
But then when we need to deliver the amplified signal to the blue pill, we thought that the blue pill has to accept it within the voltage range of 0 to 3.3. So wouldn't there be a negative component of the voltage that gets missed? Or
yes, yeah. And in the circuit we were just looking at, that negative component gets chopped out by the Zener diode.
Right. So then would we have to reintroduce like a fixed DC offset so that the entire analog signal can make its way into the blue pill? Or?
Yeah, that's right. If you want to do it right without losing any of your signal, then you have to shift it, and that's a real problem, right? Because the blue pill's input goes from 0 to 3.3 volts, so somehow you have to center a sine wave around 1.65 volts. If I did that right in my head, anyways. Right, so that if you're going to capture the entire sine wave in the blue pill analog input, it has to be centered in the middle of 0 to 3.3. Yeah, and then another circuit is required for that.
Okay, sounds good. Thank you.
Yeah. Anyone else want to take a shot at it? I mean, it doesn't have to be right. I'm just curious to see what people's thought process was. No takers. It's not obvious, eh? I mean, the circuit that does all the things I just described there is actually relatively complex. Last call for anyone wanting to try? Everyone's shaking their heads. No bloody way.
And then just one question regarding, and I forgot his name, that showed the circuit before. What gets that capped discharge? So he had 5 volts through the photo transistor and then into a cap. So I can see the cap charging up to 5 volts, but then what discharge is it so you can get a...
I think that's where I was struggling as well, Meaty, yeah. I feel like it saturates the capacitor in a way that it can't come out of saturation.
Yeah, that's a good point that was not taken into consideration.
Yeah.
Yeah, I think you're totally right.
But that, I think that's a pretty good crack.
No, I was going to say you're 90% there, yeah.
Yeah, thanks for bringing that up, Meaty.
Anyone else? I know this is a long shot. Okay, all right. I will go ahead and show you what I came up with then and walk you through it. And which is this. So this looks significantly more complex, and part of the reason for that is I'm using a single 9-volt battery. Let's see if I can, okay, my mouse is working now. So let me start with the power setup, okay? So I have a single 9-volt battery, so there's 9 volts here, and there's ground here. If we're going to have an oscillating signal around ground, but we're limited by the fact that we don't have any negative voltages, we have to make a new ground. So what I've done is made a resistor divider to create 4.5 volts. Right? Now that 4.5 volts here is very fragile, because as soon as I draw current from it, would shift away from 4.5, because current would have to flow through the resistors. You get Ohm's law sort of voltage changes. So what I've done is I've replicated the 4.5 volts through a buffer to make a stable 4.5 volts that I can actually sink current into and draw current from. And this 4.5 volts is effectively my new ground. So these op amps are powered between +9 and 0. This is +9 and 0. And this artificial ground is now, so it's now like the op amps are powered from +4.5 and -4.5. All right. So if you want to do this with 2 9-volt batteries, you can get rid of this op amp, get rid of this resistor ladder, and just run the op amps from +9 to -9, right? But this is a trick that allows you to do this with a single 9-volt battery. All right, so that's that complexity of these resistors, this amplifier. That's for that reason. beyond that, I've just got the phototransistor and a load resistor, right? Again, it's going to the new virtual ground, or sorry, the new artificial ground, but you know, that could be a regular ground if you use 2 batteries. And then I'm using a buffer so that I can pick up this signal and put it through an RC filter without loading down the phototransistor with a capacitor resistor combination, you know, whose behavior with the phototransistor I wouldn't necessarily be able to predict, right? So again, this for me is a conceptually easy way to do it. I'm doing it in stages. I'm like, okay, here's my signal, simple phototransistor resistor combination. I'm pulling off the signal, I'm putting it through a buffer, and then putting that through an RC filter. And then I'm amplifying that with a non-inverting op-amp. All right. Then I'm doing what Rudranj was just talking about. Like I now have, at this point in my circuit, I now have a sine wave around ground, okay? So here the signal looks like this. Okay, I can't draw sine waves with the mouse, but it looks like that. Here, it looked like this. Right? So I've shifted it down around ground, and I've amplified it actually, so never mind. It should actually look a lot bigger. Anyways, you get the point, right? But it's around ground, which is not really ground. It's around 4.5 volts. What I need to send to the blue pill is this sine wave centered around 1.5 volts. So what I've done is capacitively coupled it, right? So I'm basically putting it through another DC block, right? A high pass filter that couples into a resistor divider that centers the waveform around 1.65 volts. And I'm still protecting this with a Zener in case the waveform was big enough to drive the voltage at this point above 3.3 volts, right? But this part here effectively level shifts it, okay? So it's shifting from being around 4.5 volts to being around 1.65 volts, and then it goes to the blue pill. Does that make sense?
I have a question about powering the op amps here.
Yeah.
So we use a virtual ground of 4.5. That makes sense. And then, so when you power it with essentially 0 to 9, right? Then it's the same thing, but with half the voltage range in the power. So, like as the case when you had two batteries.
Yeah.
Right. So earlier we were talking about how you want to power it with much more than you expect to get out of an op amp. So that would affect that potential highest output you could reach here? That's
correct. But if you look at the output stage, I only need the maximum. I want my sine wave to the maximum excursion in voltage I want in that sine wave is plus minus 1.5 volts roughly.
Yeah, fair enough. Yeah.
So with the op amps being plus or minus 4.5, I've got enough headroom.
Okay.
Yeah. And I think someone was asking in the chat, where did the chat go? How this works. And think about this. So a DC, this should be straightforward, right? A DC, you can forget this this capacitor. And what you've got is a voltage divider setting a voltage at the point that's circled. That's 1.65 volts, right? So a DC, that's fine. As sine waves come in through that capacitor, basically the current associated with that sine wave impacts this voltage, and it'll shift it up and down. You know, by how much depends on the size of this capacitor and the size of these resistors, but it will drive a sine wave into this node that you can detect with a blue pill. You know, it's almost like, imagine that you did this mechanically. You had a rubber band to the top, a rubber band to the bottom, and then you got something jiggling this point. It's going to oscillate up and down. So yeah, so this is a level shifter circuit, basically. I mean, I just did that off the top of my head, but I'm sure that's a commonly done thing.
I have a question.
Yeah.
Instead of, so like you're using a voltage divider with just two resistors, and then you have like these buffers.
Yeah.
Would it be easier or possible to use like a Zener diode as a linear regulator, like to regulate it to 4.5 volts or something?
Yeah, absolutely.
Like, and then you wouldn't need the buffer op amps.
Yeah, and you're talking specifically around this one, right?
Yeah, or yeah, I guess not the second one, but yeah, the that first one. Because if you had a Zener diode, then you wouldn't need to buffer it because it would have
Yeah.
an IA.
So first of all, and meaty, yes. Let me come back to that. So I believe they sell chips that do this for you, that create a artificial ground for you. And the advantage of something like that is current draw. So if you run a 9-volt battery into a Zener diode, you're going to be dumping a ton of current through that diode as it tries to force the voltage down to 4.5 volts. You can put a resistor in front of it, but then you're still dissipating heat in that resistor, right? This is sort of this draws less power, because unless you're actively dumping current into this op amp or drawing current from the op amp, which you're not going to seriously do here, right? Because there's small currents, it's just signals, right? Then you're not dealing with a lot of power consumption, which otherwise you would be dissipating in the Zener diode.
Okay, that makes sense.
Yeah.
But I guess if you were drawing, in this case, you're not drawing any current from the power source. But if you wanted to use, like, for example, this 4.5 artificial ground as like the global ground for your circuit, and you wanted to power things,
and if you were, yeah, right? No, absolutely. This is only good as a signal ground. If you're dumping real amounts of power in there, like through a light bulb or a motor or something, then we're getting back to the realm of having a voltage regulator, not an artificial ground.
Okay, yeah, that makes sense. Thank you.
Yeah. And the filtering, the questions on filtering. Yeah, absolutely, right? I mean, you can work out the RC time constant that is 33k ohms. In fact, the time constant is probably, 16.5k ohms times 470 nanofarads, because these two resistors are going to be in parallel as you work on the time constant. And I haven't done that off the top of my head. I'm sure I did that when I was designing this circuit, but I'm sure that time constant is compatible with allowing 1 kilohertz and above through, which would be the important part. So I'm planning to use this, of course, and built it to be used with a 1 kilohertz or a 10 kilohertz beacon. So as long as those signals make it through this part, then you're okay. The other problem we'll talk about, like I said, another day. There is an additional issue that could come up here of high frequency aliasing, but that's for another lecture. Any other questions on this? Okay, it's 5 o'clock. There are more slides, but I'm not going to cover them today. You'll see them posted when I post these slides. There's a little bit more around actually frequency detection, but I will cover that at the beginning of the lab on Thursday. So please make sure you come right at 2 o'clock on Thursday, and I'll cover the last 3 or 4 slides to explain cross-correlation as a method of frequency detection, and why you need frequency detection at all. Obviously, the reason we're doing all this and trying to detect a pulsing beacon is so you can tell it apart from noise in the room, right? Because if you make a 10 kilohertz beacon, unless you're really unlucky and something else in your kitchen is creating 10 kilohertz infrared, right? You can home into that 10 kilohertz and it'll be a unique signal, right? But to do that, you have to measure that it's 10 kilohertz, and we'll talk about that on Thursday. So yeah, I will let you all go, and I'll see you tomorrow for the TechCom lecture, which will be really design help. Okay, so please do drop in, but and come ready to go into breakout rooms and get my help and anyone else who's joining me in terms of design.
Design help for the robots, right?
Yes. Yeah. Also happy to chat about your mechanism deconstruction if that's if you're working on that, whatever you'd like. All right. Excellent. Thank you all.
Recording